All right, so these are the main things that we're going to talk about in week 9. But before that, I just want to clear up two small parts, yeah, before we go into this main topics, right? So the first part is on just to give you a better idea of how to work with this sort of sets, right? So the limit supremum of sets, right? AN is defined as the following. Okay, because we are going to use this result later, yeah. Okay. So, and of course, the limit infimum will be the opposite. So you take intersection first, and then only you take the union, right? So these are, of course, we have already looked at the tutorial that these are definitely in the sigma field of your probability triple, and therefore you can assign a probability measure, right, to these sets. Okay. So here I just give you something concrete, just to make the idea a bit more concrete, right? So let me clear the screen. Okay. So let's look at one example here. Suppose you have a line, 0 to 1, okay? And you make the following sets, right? So you make this set from, you go until 1/2, right? This is your A1. For set A2, you take from 1/2 to 1, right? Then after that, when you do A3, you take from 0 until 1/4, and then you take, right? So for A4, you will take from 1/4 until 1/2. A5, you take from 1/2 until 3/4. And A6, you take from that, okay? And after that, you will have your A7. Basically, you will repeat, you just cut this into half. A8, A9, A10, and so on, yeah? So you will have some sets like this. Okay? All right? So this is how your sets are generated in this way. So let us ask the question, what is the set lim sup AN? So this by definition is the intersection and union of AK. K goes to N goes to 1, right? So basically this involves the following. You take a K starting from 1, right? So you sub in N, and then you take the intersection with the second set, which starts from 2, and you intersect with the set that starts from 3, and so on, right? Keep intersecting. Now, you take 2 minutes to look at this intersection of these sets, right? What will it lead to at the end? What is this set? Okay, so what should that set be?
Limit of AK approach infinity.
Sorry, it is a set here, right? These are all sets, right? So you're taking intersection of sets. So if you take countable intersections, it will lead to one set here. What is this set? I mean, refer to this set here, right? The set. So this your A1, A2, and all that are subsets of this 0, 1 interval, right?
I think should be summation of 1 to k, 1 to infinity ak.
Huh? Summation?
Yeah.
Why does it involve summation? I mean, this is set operation, right? You have sets, so you take intersection, right? So, why would it involve summation?
I want to sum them up.
You cannot sum set operations, right? You can only take union, and you can take union, intersection, complements. Here it's just you're not applying a probability measure yet to this thing. So it's just operating on set. It's just set operations. So there's no summation.
Okay.
Is it will become an infinite small set, like a very small set?
Okay, you look at this thing first. What is this set? The union of, if you take the union, countable union of AK, what will you get? Empty set. Really? What is this set? You take A1, union A2. So you don't have to care about the union of the rest already, because so this guy is already your 0, 1, right? Isn't it? It's got A1, it's got A2, you take the union, it already forms your 0, 1. So this is 0, 1, right? And how about if you start from 2? If you start from 2, so you don't have, so if you start from 2, you don't have this one, right? You start from 2. So you have 2, you have 3, you have 2, you have 3, you have 4. Doesn't matter anymore, right? So the rest, even you have all these, doesn't matter, because with 2, 3, and 4, you already form 0, 1. So again, this is a 0, 1, right? Okay. Then you look at 3. If you start from 3, you don't have this, right? So basically, you're starting from 3, 3, 4, 5, 6, and so on, right? While 3, 4, 5, 6, you already you take union, they already become 0, 1. Okay. So you can you see that basically each of these unions, they basically just lead to 0, 1, right? Because if you start, okay, if you continue, let's say you start from A4. If you start from A4, you you have this segment. Okay, you got this segment, this segment, this segment. The part that you are not, that you missed out, right? You can cover them back with A7 and A8, right? So once you cover back already, this becomes 0, 1 again. So basically all these unions are 0, 1, and you are basically taking intersection of all 0, 1s. So clearly this is 0, 1. Okay. All right. So is it clear?
Yes, doctor.
You just look at the geometry, right? I mean, like you have to you have to use some geometrical thinking in this kind of problems, which I've stressed quite a few times. Once you look at the geometry, it's really trivial, you know. It's very obvious, right? So think of it like this, okay? Okay. So then, therefore, once you know that this lim sup is 0, 1, therefore P of lim sup AN. So you're applying a probability measure on this lim sup AN, right? So lim sup AN is basically a set in your F, and this is equal to basically your 0, 1, right? Which is your omega. And therefore, the measure for this length is, the Lebesgue measure is 1. Okay. All right. So, so later in tutorial 6, you will find another example, yeah, where you have to define what is your set. Okay, what is lim sup and what is lim if. So don't get scared by this thing, because by definition it contains some set operations, and if you work out the geometry properly, then you should know the structure. You can work out the structure of this kind of sets. Okay, once you work out the structure, then applying the probability measure on it will be quite straightforward. Okay, so this is one example of lim sup. And we will also say something like this. When we say P of lim sup AN, this is the same as writing AN I dot O. This IO here means infinitely often. Okay, so this is saying this event AN occurs infinitely often. Although this is actually quite kind of like just a different way of saying this, right? So okay, so this is just basically this is more like a shorthand for this lim sup, right? And you will sometimes find this notation. Okay, this notation I dot O, I will use it later for convergence with probability 1, right? Okay. So now I move on to the idea of independence. Yeah. Independence. So this one, I think you are actually quite familiar already. But just to make sure that we know what we are talking about when we say when we refer to this idea of independence. Yeah. Okay. So suppose you have you define some probability triple, right? Okay. Let A1, A2, AN be elements of your sigma field, right? And we say that A1, A2, AN are independent. If and only if if and only if the probability that you take AK all right, so this IJ is basically the set of n choose J combinations of A1, A2 until AN, okay? For all J equals to 2, 3, 4 until N. J equals 1 is trivial because J equals to 1 is basically only, there's only one member, right? So J equals to 1 is trivial since you basically will just have PA1 equals to PA1 and so on, okay? So J equals to 1 trivial. So basically if you want to say that these sets are independent, then you have to establish you have to check all these conditions. Okay, so you have basically quite a lot of things to check if your N is large, yeah. All right. So the most common at the elementary level, of course, you have this thing, right? If A1, A2 are independent, then PA1 intersect A2 is PA1 times PA2. Okay, so okay, you check this. If this condition is true, then it's independent. How about if there are 3 events? Okay, if there are 3 events, you will have to check 2 things, right? Because over here, you will have 3 choose 2 and 3 choose 3. So 3 choose 2 will consist of, you have to check. So if you have 1, 2, 3 here, so this will be, you have to check A1, A2, and A3, right? So 3 choose 2, then you will have to check the others. So you have to check A1, A2 is equal to this. A1, A3 is equal to this, the product, yeah? And A2 and A3, right? Is equal to that, okay? So only when all these conditions, this one and these conditions are fulfilled, then only you can say that your A1 until A3 in this case are independent, yeah? Okay, so you have to check more conditions when your AN is different. You cannot just check pairwise. Huh? A lot of people, they will say that this is true by checking all these pairwise. No, it's not enough, right? You have to check all these parts. So suppose, let's say you have another example. Let's say you have A1, A2, A3, and A4. You will have to check these things. PA1, A2. Okay, you check this until 3, 4, yeah. So how many will be there? There will be 4 choose 2 to check, right? So there are actually 6 things to check here. And then number 1, number 2, then you have to check this A1, A2, A3. All right, and so on until the last one will be 2, 3, 4. Okay, so there will be 4, choose 3, so there will be 4 things to check here. And finally, the last one will be A1, A2, A3, A4. It's equal to the product of the respective probabilities, right? Okay. So you got to check quite a lot of things. And therefore, if any one of them is not true, then this whole set is not considered to be independent, all right? Okay, so this is just some extension of the notion of your independence to more than two events. Okay. Okay, so now I'm going to talk about the notions of convergence. So I have number 1 is called convergence with probability 1. Or sometimes this is called almost sure convergence. Number 2, you have convergence with, convergence in probability. Number 3, you have convergence in distribution. Okay, so there are these 3 notions of convergence, and there is actually a hierarchy among them. So if you establish convergence with probability 1, then this would imply convergence in probability, and it would also imply convergence in distribution. Okay, so the flow is from 1 to 3. Yeah. So if you establish convergence in probability, you can claim convergence in distribution. However, you cannot claim the converse is not true. So you note at the direction of the implication. Yeah. Okay. So convergence with probability 1 will imply the other 2 convergence modes, but the converse is not true, right? You cannot go backwards. If you have convergence in distribution, it does not mean that you have convergence in probability or convergence with probability 1. All right, so these are the 3 notions, yeah? You may have come across them in year 2, but maybe it's just glossed over. Okay, so I think probably you may have come across these 2 things, but this is definitely new because this concept involves the use of the lim sup, right? The lim sup and the lim inf of some sets, right? Okay, so let's look at the first one, yeah, convergence with probability 1. Let's look at the definition. Okay, convergence with probability 1. Okay, so let x1, x2, xn be a sequence of random variables. Sequence of ID, yeah? Independent and identically distributed random variables. Defined on, so you need your probability space, right? The probability triple. We say that xn converges to x almost surely, so we'll write A dot S, almost surely, if and only if we have the following. Goes to 0, which is equivalent to the following, yeah? Infinitely often. That is. No, sorry, this one should be wait, this should be the limit. No, not sorry, not this one, not this one. Okay, sorry, that was not correct, the previous text. That was for convergence, the other convergence, right? So this is equivalent to P of lim of this. Sorry. Okay, so when you say convergence with probability 1, it means the two things, yeah? So it means that the limit of the sequence of random variables here, as your n increases towards infinity, okay? So the measure, yeah, the probability measure on this set here is equal to 1, okay? Technically, it means this. Okay, this is actually not so useful. This is more for writing, but technically, this is more meaningful. Okay, it basically says that this xn, right? This is your random variable xn. As your n increases, it gets closer and closer to the chance that it gets. So so xn minus x is the deviation, right? Okay, so this set. This set being the deviation here being larger than or equals to epsilon, where epsilon is some arbitrary constant that's larger than 0. This happens infinitely often. Okay, right? So this is kind of like escaping. Your xn escaping from x. Okay, by more than certain amount infinitely often. The chance of this happening is 0, yeah. Okay, it's impossible to escape from x infinitely often. That means it can escape, but only for a finite number of n's, right? And not infinitely often. Okay, that's why you have the term here almost surely. Okay, so it cannot escape from x by more than a certain amount infinitely often, right? Keep on escaping. Okay, so this is this definition is actually quite abstract. So we'll just take it at the moment as this, yeah. Okay. So later this Convergence with probability 1, later we will see how to use it in the proof for the strong law of large numbers. Okay, so the strong law of large numbers concerns this result. Yeah. Okay, so this is convergence with probability 1. And then the next thing we have convergence in probability. Okay, again, the IID random variables defined on the probability triple. We say that xn converges in probability, so we write like this to x, if and only if the limit, okay, is of this is equal to 0, right? So basically, this one you are saying if this, so you first find out what is this probability measure, and then you take the limit, right? If it's equal to 0, then we say that xn converges in probability to x. Now, what this means is that you are saying that the chance that your xn, right, escapes from your x, by more than a certain amount, yeah, by more than epsilon, that probability will vanish, yeah. Okay, that means in the limit as your n becomes more and more, right? The chance that your xn escapes from your x, right? This x can be some random variable, is some random variable, but it can also be a constant, right? Okay, so it escapes from this x by more than a certain amount. Epsilon is 0, yeah. So it can't. That probability diminishes. Okay, and in order to show this, this is technically easy to show because we have Chebyshev's inequality. So technically, you have to use Chebyshev's inequality to show this result because by Chebyshev's inequality, so suppose this is let's say this is the expectation of x, yeah, x yeah, I think you can put expectation of xn more than or greater than epsilon is bounded by the variance of xn, okay, over epsilon square, okay, and of course the lower bound is 0. So basically your upper bound here, it concerns the variance of xn, and usually this will involve some kind of n in the denominator, all right? So, and therefore as your n tends to infinity, your upper bound here will tend to 0, yeah? Okay, when your upper bound tends to 0 and equals to the lower bound, that means this limit is true, yeah? Okay, right? This probability becomes sandwiched between two values, which are the same. So indicating that you have the limit at this point, yeah, at equals to 0. Okay, so the simplest example here is the following. So if you have Consider the following. Okay, the sum, yeah. Consider the sum. Then the Sn over n, right, minus mu, right? So this mu, right, okay, if you take expectation of Sn, this is equal to the n of expectation of x1, right? Because of, so here you have IID x1 until xn. So since they are IID, you can use one of them. So this becomes an n of mu, right? So suppose I have expectation of x1 is equal to mu, right? So therefore, so expectation of Sn over n is mu, okay? So this fulfills the, so you have one random variable here, and this is the expectation of this random variable, right? And therefore, we can use Chebyshev's inequality, right? So the probability that this Sn over n, right, escapes from mu by more than a certain amount is therefore bounded by the variance of Sn over n over epsilon squared, right? So the lower bound is 0. So over here, you will have n squared, epsilon squared, right? This is a constant. So variance of Sn is, you take the variance of Sn, that's equal to n times the variance of x1, right? So this n sigma squared, okay? N sigma squared. So you cancel off the n. So basically you have a denominator of n here. And therefore this will tend to 0 as n tends to infinity, right? So therefore we say that Sn over n converges in probability to mu, right? Or you can simply write Sn over n converges to mu p, okay? Right? When you make this statement, so you have to show this technical result, yeah? And this technical result merely applies your Chebyshev's inequality, right? By showing that the upper bound, yeah, of this quantity converges to 0. Okay. So basically, what happens here is that if you notice this carefully, this is your ray sample mean, right? Yeah, the sample mean. So essentially, it is saying that your sample mean, right? The sample mean converges in probability to the population mean. Now, this is a very powerful result as n tends to infinity. It's saying that your sample mean, right, is a reliable, using the sample mean to estimate the population mean is a reasonable thing to do, because as your sample size increases, yeah, it will get the chance that it deviates from the population mean by more than a certain arbitrary amount is going towards 0, right? It becomes almost impossible, okay, for it to escape from the population mean when the sample size increases, okay? So that's why sample means are used so often, yeah, to estimate the population mean, right? But of course, this is presupposing that you have obtained your x1 and x2, right? They have to be IID, right? Okay, that means you have to have some randomization mechanism, because otherwise, if you have a biased sample, then this result doesn't hold. Yeah. So this result holds supposing that you have some randomization. Okay, your x1 and x2, they are all randomly picked from some underlying distribution. Okay. All right. Okay. So this is convergence in probability, and the last one is convergence in distribution. Okay. So again, you have x1, x2, xn, right? Being IID random variables. From from a probability triple. So we say that your xn converges in distribution to x. So we denote it like this: if and only if fnx is equal to fx. Okay, so this is the distribution function of xn. This is the distribution function of big X. Okay, so which basically is saying that this statement only concerns the distribution function of xn. Yeah? It's saying that as your xn, as sample size increases, your xn becomes, the distribution of xn becomes closer and closer to x. The most famous example for this convergence in distribution is your let me see, it should be your central limit theorem. Right. So the central limit theorem says that if you have x1, x2, xn, IID with finite mean and variance, yeah. Okay. Then you take the sum. So I'll denote Sn as the sum. Yeah. So the sum, so the average, minus, so we finite mean mu and variance sigma square. Okay. You take the sample mean, subtract the population mean, and then divide by the variance of Sn over, sorry, the standard deviation of Sn over n. That will be the sigma over square root of n. So this one, this quantity here converges in distribution to the standard normal. Okay. So this is an example of convergence in distribution. Yeah. So the distribution of this quantity here, right? Okay. In the limit, it becomes a standard normal. Yeah. Okay. So basically, given any sort of distribution function here, we can find out what is its what does it converge to. So let me give you an example here. So suppose you have we we have x1, x2, xn from uniform 0, 1. Okay, so then let's look at this quantity n. Let me see. This should be, let me, instead of the max, I think it's the min. Okay, so that should be 1 minus, okay, because you have uniform distribution, so 0, 1, this is y over n. So you want the area under the curve here, right? So it's 1 minus y over n, okay? Therefore, the distribution function will be equal to 1 minus of this, okay? Right, so you can think of this as one random variable yn, yeah? Okay, yn. Okay, so this is my f and y, okay, is equal to this. And if I take the limit, this will be taking the limit. Okay, right, so what will this limit be? Can somebody tell me? What is this limit? Anyone? What is this limit?
One minus the power of negative y.
Okay, 1 minus e to the power of minus y, right? Yeah, because this is just basically a constant. So this is a well-known calculus result, right? So that's why you have to know this this limit. This limit is very important. Okay, so you get this function. So this is the CDF of what distribution? Of what distribution? Do you recognize? Which distribution has a CDF that's given by 1 minus exponential of minus y?
Exponential.
Exponential distribution with what parameter? Parameter equals to what?
With lambda 1.
Okay, with lambda equals to 1, yeah, with mean 1, right? So if you have an exponential distribution with exponential with lambda equals to 1, sometimes you have to be careful when you mention the exponential distribution. When you say an exponential distribution with parameter lambda, it's written like this. Okay, the PDF is written like this. If you say it's an exponential distribution with mean lambda, it will be, if you say it's mean lambda, then it's 1 over lambda of this. Okay, so it will become the reciprocal, yeah. Okay, so these are basically, I mean, like basically they are just different ways of specifying the parameters. Okay, so just be careful, right? If you have parameter lambda, the mean will be 1 over lambda. Okay, you can check that by doing the integral. Yeah. So over here you can see that this is definitely so basically this is 1, right? Lambda 1, right? So we take integral. This is basically 0y. So this 1 minus e of this, right? So basically, this is the CDF of the exponential distribution with lambda equals to 1. Okay? Which means, in a nutshell, n times the mean of x1 until xn converges in distribution to an exponential 1 distribution, yeah? Exponential distribution with parameter lambda equals to 1, yeah? Okay, so this is an example of convergence in distribution where you use mathematical statistics to show, yeah? Okay, so if you have, just to recap, so if you take RID random variables from a uniform distribution, you find the minimum of them, and then you multiply by the sample size n, yeah? So this will create a random variable y subscript n, okay? This subscript n basically denotes the sample size here. This random variable will converge in distribution to the exponential 1, right? When your sample size increases, right? So which means if you take more and more, yeah? So its distribution, yeah, will be in the limit like the exponential distribution. Okay, so this is where we can say claim convergence in distribution. All right. Okay, just a minute. Yeah, I have a call from the office. Okay, sorry, just now the office has some matters. Okay. Right, so I think, so these are the three things that I want to talk about for notions on convergence, okay? So we'll take a 10-minute break. After that, we come back, we will look at the two important theorems, yeah? They're called the strong law of large numbers and the weak law of large numbers. Okay, so let's get started again. So now I'm going to talk about this major theorem. This is called the strong law of large numbers. So let me state the theorem first, yeah? So let x1, x2, xn be independent and identical, yeah? And identically distributed. Random variables with mean mu. Okay. And let Sn be the sum, right? Then okay. So basically it's saying that Sn over n converges almost surely, okay, with probability 1, yeah, to mu. All right. So again, this is a result that tells you that using your sample mean to estimate your population mean is a reasonable. In fact, it's guaranteed that your sample mean will converge almost surely to your mu. Yeah. Okay. And technically, so we need to establish this result. Okay. Right, this is reassuring because you know that as you take a larger sample, you take more samples, then your sample mean will be closer and closer to your population mean, right? And again, please take note that you have IID situation, yeah, which means you must have some randomization mechanism to obtain x1 until xn, right? If you have a biased sampling scheme, then of course this theorem will not hold. Yeah. Okay. So let's look at the proof. The proof is very interesting because it illustrates the connection of many techniques together, right? So we will study the proof. The first thing is without loss of generality. To simplify the matter, we can assume that mu is 0. Okay. Okay. So in general, it holds for all mu, but there's no loss of generality even if you assume it to take some particular value, right? So we'll work with 0 because then things are easier. So we need to show that. So equivalently, this statement is the same as showing the following, right? Exceeding epsilon infinitely often is equal to 0, right? Okay, so remember earlier that we declared the equivalence of these two equations, yeah? So infinitely, so when you say that the probability that the limit of Sn over n equals to mu, this probability is equal to 1 is equivalent to saying this statement, yeah? Okay, so now we need to make an assumption here. The second and fourth moment of x1, xn exist, okay? And so we have expectation of xi square. So this is the second moment is equal to sigma square. And the fourth moment is equal to psi. This is read as psi. Okay, psi power of 4. So all these are definitely positive, yeah. Okay, so to get started, we assume these two things. Later, you will see why this fourth moment was assumed. Yeah? Because of the need to use Markov's inequality. So you have to assume this moment. Okay, so we assume that these two moments exist. So now we want to show the following. Okay. Okay. Remember, my Sn is equal to the sum, yeah? All right. So the expectation of the sum to the power of 4, this is of course equal to so this thing, yeah? Okay. Now, if you expand these things, you will get the following. So you have your x1, so there will be power of 4, okay? So then you sum 1 until n. Then, yeah, so over here you will have all sorts, yeah? You have power of 4, power of 3, power of 2, and power of 1, and then power of yeah, so until power of 1, right? So then the others you will have summation xi power of 3 j k. So you got I j k. Then you have I square actually there's maybe just to, so this will be ijk, right? Be ij, and then you sum so sorry, so without that ij only. And you have xi, xj, xk. So you can have 2 here. So ijk. You can also have a k here. So ijk. And finally, you have everything, ijkl, okay? Right, so this will consist of all the expansions, yeah? The fourth power expansion, right? So you have power of 4, then the total is power of 4 as well, but you distribute the 4 to different combinations. So you have, actually there's another one here. Okay, and now don't get scared by so many of these terms, because in fact you only need to consider these 2 terms. The rest of the terms, right, these terms, right, they are all 0. They all become 0 because remember, you have your x1, xn, they are ID, right? So when you have expectation of these things, yeah, xi power 3 ij. So basically this will be just, you can split them out, right? Because they are independent, yeah. Okay, so your xi and xj can be written like this, and since your mu is 0, right? So expectation of xi is equal to 0 for all other i's, right? So basically this will become 0. So you can see very clearly that as long as your xi's are existing like by itself, right? Then the expectation of this term, no matter how complicated, will always be 0, because you can write it as a product, right? And the expectation of the single variable here is equal to 0, right? So it will disappear. Okay. So yeah, so you can all this will disappear, and you only need to consider these 2 cases. Okay. So with that, things become simple. So I can now remove all these things. Okay, so they all become 0. Okay. Now, so just now we, so over here we have, so n of them, right? And since we made a hypothesis about the existence of the 4th moment, so this will basically be n psi power of 4. And over here, yeah, so your xi and xj are independent, right? So you basically can write as the product, and this will be sigma square times sigma square. So this will be sigma power of 4, right? The only remaining thing is you want to sum, you want to find out how many of such pairs are possible, right? Sum ij, right? So how many pairs are possible? I claim that the number of pairs possible here will be n choose 2 times 4 choose 2, which will be equal to the following: n minus 1 over 2 times, this is 6, right? So this will be 3n n minus 1. Okay. So now you are wondering, how do you get this thing, right? Okay. So first thing, you look at this structure here, right? So you have got, so you got x I, xj, right? So this is how you can actually, so maybe I put a label here. So this is how you can get your xi square and xj square. So this one I label I just put a label on it, right? Okay, so 4 choose 2 denotes the number of ways, right? You can rearrange this, you can rearrange the terms here, okay? There are 6 ways that you can rearrange, and basically ignoring the order of the same object, right? So since there are 4 boxes here and your I is considered a type, J is one type, so basically it's 4 factorial over 2 factorial, 2 factorial, right? So this is the number of ways you can have arrangement for a particular ij, right? This is where your 4 choose 2 comes out. The n choose 2 basically is coming out from, because you have got 1, 2, 3 until n random variables. So 1, 2, 3 until n, right? So n choose 2 basically is talking about this part here. Right, so 1, 2, 2, 1, 1, 3, 3, 1, right? So this is n choose 2 because n choose 2 is n minus 1 over 2. Basically, this is your n square minus n divided by 2, right? N square is the whole thing, the whole square here. Subtract n, right? The n is basically the diagonal, okay? And so you divide by 2 because your 1, 2, and 2, 1, right? They're basically the same type, right? So we don't bother, so we only take half of it, okay? Right? So these are the number of combinations that you have. N choose 2, and then after you have that combination, you rearrange. Right? Internally, you can have 4 choose 2 rearrangements. Okay. So that's why you multiply them together, so you get 3n times n minus 1. Right. So when you sum, these are the number of. So this is a constant. So these are the number of ways you can sum it. Okay. So once you have these two results, so you know that this expectation is equal to n psi 4 plus 3n n minus 1 sigma power 4. Okay. All right. So now over here, we want to form an inequality. Right? So over here, this is bounded by kn squared. So this k is a constant. All right. So you look at this part here. So this is actually a quadratic term, right? This is actually a quadratic term because over here you will have 3n squared sigma power 4 minus 3n sigma power 4 plus n sigma psi power 4, right? So essentially it's actually a quadratic equation, right? You can always find some kind of, since it's a quadratic equation, you can always find some kind of constant k here such that when you multiply with the primary degree here, right? So it will be dominated. Okay. So so geometrically, you may have something like this. For example, you may have so this thing may be something like you may have some function like this. Okay. So basically you have some function like this, right? So you can basically always choose some kind of you can choose your k in such a way that you get, so this is your k n squared. So this is your whatever here, your function here, okay? So you can always find some k such that it will be dominated, yeah? Your function here will be dominated by kn squared, all right? So now we derive an important inequality, which is we know that the expectation of Sn power 4 is bounded by kn squared. Okay. Okay. So we got this important result. So let me just write this down again. Okay. Now we can use Markov's inequality. For k equals to 4. Okay. So remember Markov's inequality is for k equals to 4. So this is Markov's inequality. Okay, so here we will have our x is as n. So instead of having epsilon, we have n epsilon. So this is bounded by expectation of Sn power 4. So since it's an even power, so with the absolute, it doesn't matter, right? So over n epsilon power 4, yeah? Okay, this one whole thing, okay? And this is where your inequality found just now comes in handy, okay? So over here, you can have a further bound, right? Because expectation is bounded by this, so you have k n squared over n epsilon power 4. And therefore, you have k over n squared epsilon 4. Okay? And now, you will apply the first Borel-Cantelli lemma. Okay? What does it say? First Borel-Cantelli lemma, you have this thing. If sum of PAN is convergent, then P of lim sup equals to 0, right? So that's your Borel-Cantelli lemma. And how to use it here? So you look at it carefully. Yeah? So over here, your AN is equivalent to this set. All right. This set. Okay. So therefore, your summation of PAN is equal to the summation of P of this. All right. And since this quantity is bounded by k over this thing, so this sum is bounded by the sum of k n squared epsilon 4, right? It is bounded by this quantity. Okay? And is this quantity convergent? Is it convergent? The sum of, so we can basically ignore the constants here, right? We can take out k over epsilon power 4, can take out. So this doesn't really matter. So whether it converges or not depends on n only, right? So what is this sum? Does it converge?
Converge to 0?
Converges to 0. Are you sure? You write like this. This is 1 plus 1 over 2 square plus 1 over 3 square. How can it converge to 0? The minimum is 1 already.
Converge to pi square over 6.
Yeah, that's right. There's actually this is a well-known result. Okay, this is the so-called P series. In calculus, have you studied this before in your advanced calculus? This result, P series. You have this result. This is a power series. Yeah. Sorry, this is n. So you know that if your P is 1, right? So it's a harmonic series. So if P is 1, this series will diverge. Okay? And P larger than 1, it will converge. So it's an important result in calculus. And for specific values of P equals to 2, you have the sum of reciprocal powers, yeah? So this one has a known result. It converges to pi square over 6. You can just use that result. It's a very nice result. If you are interested to find out how they actually got pi square over 6, this is also something called the zeta function. You can do some search on that, right? But we will just use the fact that it converges to pi square over 6. So therefore, you know that this sum, right, is bounded by k pi square over 6 epsilon 4, right? So this is finite, right? Okay. So therefore, we verify that this condition is the sum of PAN is finite. And once you verify this is true, then it implies that P of lim sup of this thing, yeah. So this is true, right? And this is equivalent to okay. So this is true, and therefore this implies that it's infinitely often. Yeah? Okay, exceeding this infinitely often is equal to 0. Okay, because lim sup of an, right, implies is the same as an infinitely often, right? So you can see here that the way to prove this result relies on the use of it connects several important things. So it first tries to make use of the Markov's inequality, but at some unexpected power, right? Power of 4. The reason why I use power of 4 is because they want to. So you see over here, you see. So if you just use power of 2, right, you can't show because the denominator, right, if it's power of 2, then this will be just 2. So it will be you will not be able to. So the bound is too loose already. Okay, so not suitable. That's why you settle at 4. You settle at 4 because if it is 3, right, you are not sure. If it is 3, the expectation of this 3 is actually not easy to do because of the absolute sign here, right? It could be, it's just not easy to do, yeah, because then you can't work with x, but you have to work with absolute of x, right? So I choose 4 so that the absolute sign basically is not important, right? So that's the idea, right? Maybe it's clearer now. So once you have this bound, right? You've got this bound, then you have to connect it to the Borel-Cantelli lemma, okay? Right? Where the essential connection is this part here. So this is your strong law of large numbers, yeah? The proof. Okay. So once we got the strong law of large numbers, we will now show the weak law of large numbers. Okay, so the weak law of large numbers uses this one is a convergence in probability. So the strong law of large number implies the weak law of large number because this uses the convergence with probability 1, yeah? So it can imply the weak law. This is convergence in probability. Okay, that's why it's called the strong and the weak. Okay, so the statement is very simple. Let x1, x2, and xn until xn be IID random variables with mean mu. Yeah. Then this so of course your Sn is the sum. Then this is the sample mean, right? Then the sample mean converges in probability to the population mean. Yeah. The proof is very simple. So basically, you have this. Okay. So we know that this is lower bound is 0. System upper bound is by Chebyshev's inequality. Yeah. So this one is epsilon square. So okay. So cancel off. So this basically tends to 0 as n tends to infinity. So therefore your limit is equal to 0. Yeah. Okay, because you are being sandwiched between lower bound 0 and an upper bound 0. So in the limit, it is just equal to 0. Okay. This is much easier, very easy to prove. Quick law of large numbers, just using Chebyshev's inequality. Okay. So anyway, so the idea of this, so both of them, they are basically just telling you that the sample mean, right? The usage of the sample mean to estimate the population mean is the correct thing to do, right? Previously, maybe people are just using some very vague ideas. You know, I'll just use a sample mean to, well, maybe I just use a sample mean to estimate population mean. Fair enough, right? It seems like the simple thing to do, but that is very what we call very heuristic, because you don't have a theory to guarantee that, right? Maybe, who knows, right? In the limit, when the n becomes very large, when you collect more and more samples, right, it starts to go away from the population mean. You don't know. You just have a feeling that the sample mean seems to be the right thing to do. And here, these two tier, so over here, these laws actually assure you that your sample mean is not going to go away from the population mean, right, as your sample size increases. Okay, so with this, it's completely on a firm ground, yeah. Okay, so in fact, we will just use. So the strong law of large numbers are basically just providing the theoretical justification, yeah, for using a sample mean as an estimator for the population mean. Okay, so I think that's enough theory for today. And so let's quickly go to tutorial 6. Yeah, so I haven't assigned, so we need to maybe spend 1 hour next week on Tuesday or maybe not, maybe on next Thursday, right? So next Thursday we'll do 2 tutorials together. All right, so just to catch up, yeah. Okay, so let's look at the tutorial 6. Let's assign some students. All right, okay, can you see my screen for tutorial 6? Can you see it?
Yes, can, Doctor.
Okay, so so you have, so these are basically some practice on working with the inequalities, yeah, for last week. So there are 7 questions. All right. Okay, the first one, let's look at this. You have, let x and y be the outcome of 2 independent 6-sided die toss. Find the distribution of max x, y. Find the so basically, don't get scared by this kind of max thing. Yeah, they are actually quite easy things. So basically, this one you have if you think about it in terms of a geometry, it's very easy to do. So your x result, right, is 1 to 6. This is 1 to 6, right? Okay. So then you have all these cells, right? Find the distribution of W, right? So the W is the larger between the XY value. So your XY pairs are all here in this cell, okay? So for example, if you have a max of 1, 6, it will be equal to 6, right? So 1, 6 is here, right? So it will be equal to 6. Max of let's say 1, 5 will be equal to 5, right? Maybe I put the value here. Okay, and so on, right? Now, basically, if you consider the geometry here, anything that's anything that has got 6 inside, right? From here until here, right? All this will result in max of 6, isn't it? Correct? Anything that's running in this row and in this column, when you take the max, it will result in 6, right? So there you go, you have your geometry already. Yeah. So anything that runs from this is 5, right? Anything that runs from here until here and then goes up this column until 5. So that will be max equals to 5, right? And so on and so forth, yeah? So you work out this thing, okay? So this distribution is actually quite easy to find after you notice the geometry, right? And then finding this is so easy, right? Because you know your W is just basically running from 1, 2, 3 until 6. So you can find the probabilities and then evaluate that. Now your expectation of max of this. So this one, if you know how to represent it with an indicator function, this will also be easy. So this will be equal to A if your X is less than or equals to A, right? Because it's taking the max, yeah? So this is an indicator function. Otherwise, you will take X if your X is larger than A. Right? So if you know how to, so over here, I've already given you a hint. If you write your max as the following, then this is easy to evaluate, okay? Right, okay, so anybody wants to try problem 1? If you try it, you will learn something, yeah? Okay, anybody wants to try number 1? Is Sudha here? Sudha Veni? Okay, Sudha, can you try question 1? Okay, let's try it, all right? All right, okay. So then question 2, so basically it's just using inequalities, yeah, and some calculus work. Okay. It should be simple enough for this one. Anybody wants to try this? Nobody wants to try number 2. Interesting question. Is it ohm? ND is ohm, is it? Okay, great. Ohm will try question 2. Then question 3 also okay. So simple use of distribution function method, and then just applying a suitable inequality. Right? It should be simple enough. This one. Maybe Nurul Izati want to try this. Nurul Izati. Okay, you try number 3, yeah. Okay, then number 4. Yeah, basically this one is basically just showing using Chebyshev's inequality. Very simple. It's a practice on using Chebyshev's inequality. Anybody wants to go for this? Maybe I know Madia. Can you do it? Ainur, Madia. Okay, not around. Nurul Hidayah. Okay, just try number 4, huh? Okay, then number 5 basically is just playing with De Morgan's law. Yeah. Just try out De Morgan's law. Anyone? Simple enough. Maybe Shaswani, Shahira. Okay, Shaswani will do number 5. So number 6, you have, yeah, so you have to define you'll get some practice on finding out lim sup an and lim inf an. Slightly more challenging. Lim Carmen, can you do Lim Carmen? Lim Carmen, not here. Okay, who is SIT170008? The name is not changed, so I don't know who you are. Who is that? Okay, also tune off already. A lot of people tune off. So we can, it's very hard for me to do things like that. Who is SIT180022? Also tune off. Okay. So let's see. Problem 6. How about Zishuang? Can you do Zishuang? Zishuang. Also tune off. Wow. So basically, I'm talking to there's a very small group of people only. Most people are just around, but tune off already. Okay. Eugene, are you here?
Yes, I'm here.
Yeah, you try number 6 lah.
Okay.
Then the last one, applying Borel-Cantelli lemma, right? So showing some inequality and then Borel-Cantelli lemma. Is Xinjie here? Xinjie.
Yes.
Okay, you do number 7.
Okay, I will try it.
You just try it. Okay. All right. Okay. Done. For sign this. So we'll discuss this on next Thursday. Yeah. Right. So you have some time to work on it. All right. Okay. So so that's all for today's lecture. All right. So I'll see you on Thursday.